The topic of this class is Kronecker delta notation or symbol. First, where it is used. It is used in branches of physics and mathematics. Next is why it is used. This is to make long expressions compact, to simplify complicated expressions, and finally, this notation allows elegant, short or compact writing of formulae. Let us now define Kronecker delta notation or symbol. Kronecker delta notation is denoted by delta with suffix, say I and j, and this symbol stands for 0 if I and j are not equal, and this symbol stands for 1 if I and j are equal. So this is the definition of Kronecker delta symbol or notation. Let us give examples. What will be Kronecker delta 1, 0? Since 1 is not equal to 0, its value is 0. We consider another example of delta 1, 1, and here both the indices are identical, so its value is 1. What will be delta minus 1, 5? Obviously, minus 1 is not equal to 5 and therefore its value is 0. What will be delta I2? So for I equal to 2, its value is 1, but if I differs from 2, the value is 0. A few more examples. What will be P delta 4, 4? Now since the indices are identical, delta 4, 4 is 1 and therefore its value is P. What will be P delta 4, 1? Since the two indices differ here, delta 4, 1 is 0 and therefore the value is 0. Let us try to find the value of delta 2, 3, delta 3, 3. For this Kronecker delta, we find that the two indices are different. 2 is not equal to 3, so its value is 0 and therefore the value is 0. Kronecker delta notation holds for discrete or discontinuous variables. Let us consider the number line which houses the numbers like minus 3, minus 2, minus 1, 0, 1, 2, 3, and it goes on like that. So this is the number line, and it is clear that any two consecutive numbers are separated by a gap. To move from one number to the next one has to make a jump. There can be infinite numbers between 1 and 2 or 2 and 3, and similarly for any two numbers. So the distribution of the numbers here is essentially discrete or discontinuous, and Kronecker delta is used for such variable. So Kronecker delta notation does not hold for continuous variables. For instance, again the number line, and suppose we plot x here, and we have a continuous distribution of numbers, but Kronecker delta notation will not be applicable here. That is, delta x prime will have no meaning where x and x prime are two infinitely close points. For continuous variables, we have to use Dirac delta function. We shall now study the various properties or rules involving Kronecker delta notation or symbol. Let us first mention the symmetry property. Which says that delta ij and delta ji, they both refer to equal to 0 if I and j are different from each other, and is equal to 1 if they are identical. This symmetry property will be more evident from the matrix representation of Kronecker delta notation. So next what we study is the matrix representation of Kronecker delta. Let us consider that the indices ij stand for 1 and 2. With 1 and 2 we can consider the following Kronecker delta notations: 1 1, 1 2, 2 1 and 2 2, the values of which are, this will be 1 because the two indices are same, and these two will be 0 because 1 and 2 are not same. And with this we can form the matrix let us put the values, and therefore what we get is an identity matrix, and this matrix obviously is a symmetric matrix. Let us extend the result for 3D situation where we will consider three numbers to run over I and j. Let us consider the situation where I and j take values 1, 2 and 3. So it is a 3D case, and we can consider the following Kronecker delta here: delta 1 1, delta 1 2, delta 1 3, delta 2 1, delta 2 2, delta 2 3, delta 3 1, delta 3 2 and delta 3 3, and with them we can build this matrix. Let us denote it by delta, and let us put the values. Now, along the diagonal we have Kronecker deltas, involving identical indices, which means their value is 1, 1 and 1, and the non-diagonal terms contain Kronecker delta which involve indices which are not identical, and therefore they all have 0 value, and this means we end up with an identity matrix, and obviously this is a symmetry matrix. We now move on to discuss the contraction property of Kronecker delta. Let us consider AJ Kronecker delta JK. What will be its value? So let us answer this question. Let us consider summation over J, AJ Kronecker delta JK, and let us split it into two parts. The first part let us write with J equal to K, and the other terms let us include in this summation where J is not equal to K. So there is one term here and infinite number of terms in this summation, all of which are 0 because delta JK is 0 because of this condition that J and K are not identical. But this Kronecker delta is 1 because J and K are identical, and therefore the answer is A, K, because J is equal to K. And on the left side let us write using Einstein's summation convention. According to which the sum is to be performed over the index that repeats. For this quantity we have repeated index to be J, so the sum is to be made over J, and according to Einstein's summation convention it is not necessary to write the summation J, just to save time and space. So we've got the answer, and clearly here the repeated index is contracted, and therefore upon contraction we no longer have that index J. So let us write repeated index has been contracted, and also we note that the summation on the left side written explicitly here is no longer appearing on the right side. So the Kronecker delta within a summation destroys the summation, it removes the summation. So we can write that Kronecker delta knocks out summation. One Kronecker delta will knock out one summation. Let us do a similar type of problem. What will be the value of AK delta K4? This is similar to the previous problem, where upon contraction of the repeated index J we have AK as its value, which means the answer to this problem will be upon contraction of the repeated index K, A4. So it will be A4. This is the answer. Let us solve another problem we have to find the value of Kronecker delta alpha beta, S alpha beta. To solve this problem, let us consider summation over alpha, summation over beta of the given quantity. We note that alpha index is repeated, beta index is also repeated, so there will be two summations. And let us first sum over beta. So summation alpha will be retained, and let us dissolve this summation into two parts. One is corresponding to beta equal to alpha, and the other one involves all the terms corresponding to beta not equal to alpha. Since beta is not equal to alpha, this Kronecker delta will be 0, but this Kronecker delta, because beta is equal to alpha, will be 1. So we are left with summation alpha, S alpha, and for beta we will write alpha. So this is the answer. We note again that the repeated index, that is beta, has been contracted, and secondly, presence of Kronecker delta knocks out one summation. Now what if we summed over alpha first? Then we would have obtained the same result, but now the repeated index alpha would have been contracted, and the final result would be expressed in terms of beta. So alternately, we can write, now we have to retain summation over beta and actually sum over alpha, and this gives us and now we have to sum over alpha, which is not equal to beta in this second term, and as before this is 0 and this is 1, so that we are left with summation over beta, S. Instead of alpha, let us put beta. So this is the answer. Now it does not matter whether we write in terms of alpha or in terms of beta, because alpha and beta are dummy indices or run indices. They do not have specific values, rather they take on values, say 1, 2, 3, etc. So it is immaterial whether we are using alpha or beta or any other symbol to express this sum. And according to Einstein's summation convention, we can suppress these two summations and write it as and if we use the same convention on the right side, then we have here S alpha alpha, or it can be written as S beta beta. Clearly, the answer to this problem can be written by contracting one repeated index, because one Kronecker delta is involved. So the answer is either S alpha alpha if we contract beta, or equivalently S beta beta if we contract alpha. So occurrence of one Kronecker delta will contract one repeated index. It might be either alpha or it might be beta. So the answer is either this one or that one. Let us solve another problem. Delta ij, delta jk. We note that these two Kronecker deltas involve j In other words, j is the repeated index. So it will be sum over j. So let us consider the quantity and let us dissolve it into two parts. One corresponding to j is equal to I say, and the second term will involve infinite number of terms corresponding to j not equal to I. This term is 0 because I and j are unequal, while this term is 1 because j and I are equal. So the answer will be Kronecker delta. Instead of j we will have to write I, so it is ik. So this is the answer, and on the left hand side we can use Einstein's summation convention, using which we can suppress this summation j, and therefore we have, so we see that the repeated index, that is j, has been contracted, and therefore the result does not contain any j. As an illustration of the contraction property, let us consider another problem. So we have to find the value of this product of three Kronecker deltas. Now these two Kronecker deltas have repeated index j, and therefore we can contract j, and the result is delta ik, and delta in is here. And again these two Kronecker deltas have I common, that is I repeats, which can be contracted, and therefore we end up with delta kn. So in the first step we have contracted j, and in the second step contraction of I has been done, so that we have this result. Another problem, we are required to find the value of this quantity. And we note that the index j repeats, so let us contract j. And further, this term will be different from 0 only if j is equal to I. Terms with j not equal to I are 0 because of the presence of Kronecker delta. So let us rewrite this quantity putting I for j, and therefore we get, so we have to put I for j, and delta jj is 1. So this is the answer. Now again, now a study of this term shows that I repeats, so there is a summation over I here, and also j repeats, so there are two summations, one is over I and the other one is over j. In other words, alternate expression of this quantity is putting the summations explicitly, and here we find that the index I repeats, so this in fact represents this quantity. The difference is that here Einstein's summation convention has been used, while here we have written the sums explicitly. The point that is to be noted is that Kronecker delta knocks out one summation. Here we have two summations and one Kronecker delta, and here we have only one summation, which means this Kronecker delta has destroyed one summation. Let us address another problem. We have to simplify this expression, which involves 2 Kronecker delta, and we see that I repeats, J repeats, K also repeats. So this quantity involves 3 summations. One is over I, one is over J, the other one is over K. So there are 3 summations and 2 Kronecker delta, which means the end product will contain only one summation. So it follows that the end product, that is after simplification, we will end up with only one summation, because 2 summations will be destroyed by these 2 Kronecker delta. Obviously this term will survive only if J is equal to K. So all J not equal to K terms are 0 because of Kronecker delta Jk. So let us rewrite this expression putting K for J. And delta Kk is 1. So this is what we have. Again, this term will survive only if I is equal to K or K equal to I, whichever. So let us put I equal to K only to write down the surviving terms. So let us write with I. So we have AII, BII and CII, and Kronecker delta II is 1. So this is the answer, and here we see that there is one summation only, and that is summation over I. So where did the other 2 summations go? They have been destroyed or killed by these 2 Kronecker delta. And also it is to be noted that writing I or K or J doesn't matter, because they have no significance. They do not take any specific value. They just run over certain pre-decided values, like say 1, 2, 3, etc. So it doesn't matter whether we are expressing the final result with I or J or K. In the next problem, we are to evaluate in 3D Kronecker delta Jj. Now in 3D, J, the run index or the dummy index, takes on values 1, 2 and 3. So Kronecker delta Jj, which involves 2 repeated index, is in fact written in the Einstein summation convention, and we can also put the summation sign and rewrite it. So it will be delta 1 1, delta 2 2 and delta 3 3. That is this sum, the values of which are 1, 1 and 1. So it is 3. So the answer is 3. And for n dimension, delta Jj is n, because it is actually sum of delta 1 1 plus delta 2 2, and it extends to delta nn, each of which is 1, and there are n number of ones, which means we end up with this value n. A similar type of problem is evaluate Now here we have repeated index over j, and therefore we can contract and rewrite it as, now in 2D it is delta 1 1 plus delta 2 2. This is written using Einstein's summation convention. So there is a sum, and the sum is over I, and therefore we can expand it and put I equal to 1 to get this term, I equal to 2 to end up with this term, each of which is 1. So the result is 2. This is in 2D. But in 3D, we'll have an additional term so the answer is 3. Let us find the value of in 3D. Let us contract these two Kronecker deltas, contract the index j to end up with delta ik, and then contract these two Kronecker deltas and let the contraction be over the index k, so that we end up with Kronecker delta il, Kronecker delta li, and a final contraction over the index L gives us Kronecker delta II, and this in 2D is 2, but in 3D is 3, as shown here in the previous problem. We will show application of Kronecker delta in the next video.